In the last lesson, voltage became a bit. Now we ask the next question: how do bits become numbers? Binary is a positional number system. That means each bit has a weight. The rightmost bit is worth 1. The next is worth 2, then 4, 8, 16, and so on. So an 8-bit byte is not just a row of switches, it is a row of weighted decisions. This is why the same simple alphabet, 0 and 1, can describe small counters, addresses, colors, machine instructions, and memory contents. Let us read the byte 101100101. Start from the weights 128, 64, 32, 16, 8, 4, 2, and 1. Only the positions that contain a 1 contribute to the value. So we take 128, add 32, add 16, add 4, and add 1. The result is 181 in decimal. The useful habit is this: do not memorize a random binary string. Put weights under it, then add only the active weights. Binary is exact, but long binary strings are hard for humans to read. Hexadecimal is the engineering shortcut. One hex digit represents 4 bits, which we call a nibble. Group the byte into 2 nibbles, 1011 and 0101. The first group is decimal 11, so in hex it is B. The second group is 5. Therefore, the same byte can be written as B5 in base 16 or 0xB5 in programming notation. Nothing changed in the hardware, we only changed the way we write the pattern. Now comes the important warning. A bit pattern does not carry its meaning alone. Meaning comes from the contract, or in software terms, from the data type. The pattern 11111011 can mean 251 if you read it as unsigned. But in an 8-bit signed 2's complement system, the same pattern means -5. Same bits, different promise. That is why digital design keeps asking, what does this pattern represent here? Here is the quick 2's complement example. To represent +5 in 8 bits, write 00000101. To make -5, invert every bit. 111, 110, 10. Then add 1, giving 111, 110, 11. That is the 8-bit 2's complement representation of -5. The beauty is that addition hardware can stay simple. The same adder can add positive and negative values because the encoding was chosen to make arithmetic work. So the second mental model is this. Binary gives every bit position a weight. Hexadecimal packs every 4 bits into one readable digit. Signed numbers add a contract on top of the bit pattern, so the same bits may mean a large positive value or a negative value. In the next lesson, we will use those bits as logic inputs and build truth tables for the basic gates: NOT, AND, OR, NAND, and XOR.